So we have the limit is approaching, as it is approaching C, it's going to L, okay? From the left and the right, it's going to the same spot. And again, it does not have to get there. So Evan, let's read example number 1, please.
Look at the graph f of x equals 4 minus x to the third. What value is f of x approaching as x approaches -1?
So as it is approaching -1, all we have to do is plug it in. So when I plug it into the function, I get 4 minus the -1 all cubed. That parentheses is very important. So that's going to give us 4. What would that give us then? 4 plus or minus? Plus 1? And how many is that going to give us? 5. So our statement is the limit is 5. Boom. Plug them in. Okay, now let's read the next piece to your neighbor.
Notice that in example 1, the limit f of x is -1. The limit f of x does not necessarily depend on the value at f equals c. However, it may happen that the limit is precisely in this case, the limit can be evaluated by such well-behaved functions as continuous f of x.
All right, the key phrase in this paragraph is well-behaved functions are continuous at x equals c. I'm going to give you an example that's not part of this, the one that we basically just worked on. So let's write out f of x is equal to 4 minus x all cubed. And I'm going to actually graph this to show you a well-behaved function. Let's say I get to -1, it's going to approach 5. And that we know from the previous problem. And the graph is going to look like, I'm going to try to make it pretty. There we go. So just by looking at this is well-behaved function, meaning we have 3 conditions. There's no holes. And there's no jumps.
Ms. Barkman?
What's up?
Is that an S or a 5?
It's a 5. And no asymptotes. And it is still reaching a number still, but it'll be continuous. Make sure you remember those 3 conditions: no holes, no jumps, and no asymptotes. So then let's move on to the next page. On the next page, let's see. All right, Tegan, let's read this piece right here out loud.
The limit does not exist. Limit fails to exist for 3 major reasons.
So I'm going to go ahead and define what those 3 major reasons are. If I give you an equation like this, can you automatically tell that there's an open circle here and here, goes to the right and goes to the left? Is that familiar? Yes? How many are like, I don't know where you're getting this from? Okay, so I'm going to go ahead and show you. Let's make our T-chart. So this is kind of going back to Algebra 1, which is fine. And I want to look at a few of the negative pieces and maybe a 0 and few positive pieces. Really, in the end, I think 1 positive, 1 negative, and a 0 will be sufficient. Let's plug this into this equation. We have the absolute value of -2 all over -2. When I simplify this, absolute value of any value is going to come out as what? Positive. So would you agree that's -1? Yes. Yeah? So when I plug in -1 also into that formula, it's going to give us -1. Can I divide it by a 0?
Nope.
Undefined. What if I plug in 1? What is that going to spit out? Positive 1. And when I plug in the positive 2, that's going to give us 1. So the idea is, this is 1, and that's -1. No matter what the positive value is, it's forever 1. And no matter what the negative value is, it's going to be -1. So is that better? Okay? So then, let's see our limit then. It says limit as it approaches 0. So as I go from the left and from the right, are we going to the same spot?
No.
It is jumping, correct? So let's go ahead and write out it is jumping. So that means the limit does not exist. And here's a reasoning in calculus. The way you're going to write this out is limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right. And that little positive on the power area and the negative means from the left, from the right. Yes, ma'am?
Which part is the jumping?
Right here. It goes and jumps. It's not continuous. All right, second scenario. There will be cases where the limit does exist. So let's draw this one more time off to the side. So my graph look like this. And if you want to write out -1 and +1, that would be helpful. What is my limit approaching on this one? 5. So let's go ahead and put tick marks at 5. 1, 2, 3, 4, 5. So I'm going to go ahead and put a little dot on there to emphasize where the 5 is going to go. So my limit, as I am approaching from the left and the right of that one, am I getting to the same spot? Yes, I am. We're both leading to, did I put -1 on top?
Yes.
Silly. I fixed it. There you go. So we know, yes, it is approaching the same number. The value is 1. And the way we're going to reason is the following. Limit as x approaches the 5 from the left side is equivalent to the limit as x approaches 5 from the positive side. So limit can approach the same value depending on where we're looking at it from. So now let's look at it without a graph. Y'all remember what this was called? These two functions? Hobart?
So does the negative sign just mean it comes from the left?
From the left. And the positive is from the right. Y'all remember piecewise functions? Missed it a lot, right? You're like, oh no. All right, let's see what this is representing. X less than or equal to 2 means from the left. Less than left. What can we say about x greater than 2? It is from the right. And the nice thing about these are the number that it's starting from is your x value. And we'll just need to plug it in. So when I plug in the 2 into the first function, what is that going to result in? 2. What if I plug in the 2 into the second function? 1. So just by looking at this non-graphically, are we approaching the same y value? So could we say it does exist or does not exist? Does not exist. And again, our reasoning is limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right.
What does that first word say?
DNE does not exist. It's my abbreviation. I know. My N's and M's and U's, they all look alike. We'll get used to it, right? I feel like my light blue is too light. I'll change that. Is it fine? Okay. All right, let's go on to the next one. We have something called the unbounded behavior. Y'all remember vertical asymptotes? Unbounded behaviors are vertical asymptotes. Wasn't this one of the graphs that we went over on the parent function? So let's go ahead and sketch this. Does not have to be perfect. So we have a vertical asymptote at x equals 0. And the graph is going to behave in this manner. And we have it at 0 right here. So let's see what's happening to our behavior. What is my x approaching? 0, so let's check. From the left, it's going up. From the right, it is going what? If it keeps going up, what was that number that's represented by continuously going up? Infinity, very well. But here's a little debate though. If something is infinity, does that specific number reach? No, you can also call that does not exist. The better answer will be this, but if you say infinity, I'm not going to argue with you, okay? So let's say this were a multiple choice question. I will not put infinity and does not exist together. That's not cool, okay? It'll be one or the other. Most likely does not exist. Okay, what's the next one say? Wildly oscillating, and that's going to be the following. And yes, it's going to oscillate quite crazy. It's going to go slow and go up and down, and level off. So if it is going up and down, can it make its own decision as to where to stop? No, that would always be does not exist.
Is that uniform for all?
Yes.
graphs?
For all of the wildly oscillating. Okay, more with the pictures on the bottom. Okay, Hobart, let's read this on the bottom right here. Remember?
Remember, the limit f of x does not depend on the value of f at x equals c.
So it doesn't really depend on what that number actually is. What that basically means. Look at this point. That point is represented by f of 2 is equal to negative 2. Y'all know that having a dot is called a point, right? So then when something is approaching, let's go ahead and emphasize again. Limit means it is approaching, does not have to get there. It can. So let's see where it's approaching. As we get to the 2, let's go ahead and circle the 2. As we get closer and closer to 2, from the left and from the right, am I approaching the same value? Yes. So do we have a limit? Yes, we do. As long as we're approaching, okay? So we all came from different houses or different area. We all still had a limit, right? So in this case, we have the limit as x approaches a 2 from the left is equivalent to the limit as it also approaches 2 from the right. So in this case, our limit is 1. I'm going to kind of stem off of number 2. So if you want to write number 3, because I think something else on top of that is very important. And I want you to write another question that says limit as x approaches negative 3 of the function is equal to. Just going to add on to it. Okay, on number 2, what's our x value reaching? It's reaching the 2. So I'm going to go ahead and circle the 2 so I know where I'm going. So from the left and then from the right, am I approaching the same value? No, I'm not. It's jumping, right? So we're going to say this is does not exist. And the reasoning is limit as x approaches 2 does not equal the limit as x approaches a 2 from the positive. And yes, the reasoning also could be the jumping, but I want it with the equivalent or non-equivalent. So let's change up the problem on the next one. Where is my value going to on the next question? Okay, negative 3. So let's find negative 3. And let's put a dot to emphasize it. So from my left and from my right, am I reaching the same number?
Yes.
What number am I reaching?
3.
Negative 1. F of x is a y value. And the reasoning will be limit as x approaches a negative 3 from the left is the same as the limit as x approaches the negative 3 from the right. So I want to kind of bubble off of something real quick as a reminder. All right, let's list when limit does not exist since we did a bunch of problems. Limit does not exist with 3 conditions. Okay, did our limit exist right here? Because of the unbounded or vertical asymptote. I'm going to use unbounded. Okay, let's go to our second one. Did our limit exist over here? Because it was oscillating, but specifically wildly oscillating. Uh-oh, can I fit? Oscillating. Whoa, oh no. It went over to the next page. Oopsie. And then my third one that we just did, it'll be when the left and the right does not equal, right? So the way I'm gonna write out is just left does not equal the right. Yes, ma'am.
On the third one, so how did you get negative 1?
Negative 1 came from, as we go from the left and the right, we're both approaching negative 1 of the y value. Because f of x is represented by the y value. All right, let's go to our last page. No, is that the last page? Yeah. Did y'all see the homework that I posted on Google Classroom yesterday? Did anyone open it? No? Yes, thank you. Okay?
I did, it's like CC1, CC.
Yes. So it tells you page number from our online textbook. Okay? I think I said Google Classroom post on that one. Or submit on Google Classroom. We'll see. So on number 3, let's see what's happening. What are we approaching? 0. So when you get closer and closer to 0, it's going up and down, up and down, up and down, right? What is that called? Wildly oscillating. So we're going to say this is does not exist. Now keep in mind though, that's only happening at 0. Because as I go to the right and the left, it's kind of well behaved. Okay? So let's go ahead and emphasize right here and say only at x approaching 0. Because on the right and the left, it's well behaved. On number 4, what number are we approaching on this one? So let's find where 1 is. Here's 1, and let's put a dot so we know that's the number we're about to get to. So from the left and from the right, am I approaching the same number?
Yes.
What number am I approaching? The -1. Okay, I want to do number 6 first, and then we're going to read the paragraph on the bottom that pertains to number 5 and number 8. So on number 6, what is my limit approaching on this one? Okay, so when it's approaching and I give you an equation, just plug it in. Plug it in. So when I do, I get 1 all cubed plus the 1 all over 1 minus 1. That's going to give us what over what? 2 over 0. So when I have a number like some number over 0, are we allowed to divide it by 0? What was that called? Undefined. If it is undefined, does it exist or does not exist? Does not exist. Now, in case you're like, well, show me graphically, you don't have to write this piece. I'm going to show you what's actually happening. There is a vertical asymptote at x equals 1. Because I know for me, seeing is believing, and I'm a very graphical person, so I'm going to go with this. So the graph looks like this, and it does something like this. And because it's unbounded behavior, it does not exist at that specific of 1. All right. Let's read this paragraph to your neighbor. Story time. Go. Say, hey, read to me. All right, pretty lengthy, right?
Yes.
So here's a summary. 3 things that are important. When your limit becomes 0 over 0, that is called the indeterminate form, which also means limit actually does exist, meaning we have to do a little more. So I'm going to give you an example of that with number 5. On number 5, the first thing we're going to do when given an equation is what? Plug it in. Let's do it. So we have 1 all squared minus the 1 all over 1 minus 1. That is going to give me what over what?
0.
Ooh, was that indeterminate form?
Yes.
So I want you to write something. You must do more. I know, Miss Brooks came up with this. She's awesome. Do more. So in that case, do more means typically you can factor out something. So let's see if we can factor something out. The annoying thing about the limit, until you plug something in, you have to carry that limit sign with you every single time. That's just a formality. So in this case, don't I have difference of 2 squares on the numerator? X minus 1 and x what? Plus 1. On the bottom's already factored out, which is great. Can I eliminate something? Boom, that's gone. Once it's eliminated, I could then plug it in. So now let's plug in the 1 into the remaining x. 1 plus 1. What is my limit then? 2. What that really in the end means, if you don't have to draw this piece, at 1 and at 2, there is an open circle. And let's say the graph, I'm just going to make this graph up. Maybe it might look like this. It might be a little off. As I approach the 1 from the left and the right, it is an open circle, but is there a limit? Yes, limit just means approaches. We're approaching the same spot. So with that said, let's do example number 8 with the partner. Same idea. That was a bad graph. It's supposed to be straight. Kind of straight. Done? So like, are we doing more?
Yes.
What eliminated once you did more? X plus 3. And then once that's eliminated, what am I allowed to do after? Plug in. So negative 3 minus 2 was how many? Negative 5. And again, graphically speaking, it is approaching negative 5, but there is an open circle. And again, approaching means there is a limit. All right, let's go to the last one, which is number 7. On number 7, the first thing again, when we're looking at a limit in the equation given, what do? Plug it in. It's the easy part, just plug it in. When I do, I get 25 plus 15 minus what? 10? All over, negative 5 plus the 5.
Can we also factor this?
You can factor it if you want, but the first thing I would do though is plug it in first. Because if you get 0 over 0, then factor it. Okay? All right. So just by looking at this, what's my numerator? Numerator, 30, thank you. And my denominator? And that is?
Does not exist.
Undefined, which means does not exist.